wall behind you?
Of course, of course not. No.
So it's just to hide the children going
Yeah,
around.
yes,
Yeah,
exactly. I have to close them in some box too.
They are on holidays now or not?
Not yet. They still have school, but they are at home now already.
Okay. Because in Italy, holidays already started.
Oh, then you have it good. They have school until the end of June, but then there will be some holidays, hopefully.
Yes, okay, if the COVID goes better.
Yeah.
Do you hear me?
Yes.
Suddenly it got very silent. I changed I changed rooms because we are projecting here, and the ones who are here, at least we watch it from the big board instead of looking separately in our screens. We are trying to make up for all this huge separation.
How many people are there?
We keep it up to 5 because it's because there are measures. We are still in serious confinement measures in Turkey still. So we decided will be 5. It changed a little, but many people watch it from the departments, but not from here. So physically we are 5 right now. One thing, of course, our US friends, it's a little early for them this time beginning, but are you admitting people too? Yes? Hello, Oz. Christine also came. Okay. Boguslav?
Yes.
I'm muting myself and
yes,
giving you the floor. I just want to say hello to everyone and leave the floor to our chair, Boguslav. Thank you.
Yes. Welcome to everybody. I suppose the guys in US are watching the solar eclipse. We already had it, so we can start. It's my pleasure to introduce Anna Jencova. She will talk about interesting things about entropies. This is a hot topic in many ways, and also LP spaces. Anna, please.
Okay, thank you for the introduction, and also thank you for the invitation. I really appreciate to be here, at least in this virtual way. So I would like to speak about certain versions of Renyi relative entropies and about ways how they can be introduced in the setting of Neumann algebras, using some results in noncommutative LP spaces and some properties of conditional expectations. So the Renyi relative entropies are an important family of divergences. So what are divergences in quantum or also in classical information theory? So a divergence is a measure of statistical dissimilarity of two states or quantum states. This means that it somehow quantifies the difference, how some statistical tasks or protocols are performing given the two states. And usually these measures have some operational significance, so they have some direct relations to some procedures in information theory, like hypothesis testing, for example. And they also have some important properties, so there is a longer list of them, and I will mention some of these properties, but perhaps the most important ones are, of course, the strict positivity. So the divergence should be non-negative and equal to 0 if and only if these two states coincide. So it really makes it a sort of distinguishability measure. And the second or important property is the data processing inequality, or DPI, which means that for any channel T, the divergence cannot so application of any channel T cannot increase the divergence. So what I mean by a channel, most generally a channel is a transformation between states, which preserves convex combinations of states. So it extends to a positive trace preserving linear map between the states. And usually something more has to be required, like complete positivity, because it's agreed that for such a channel to be really a physical transformation, the complete positivity is necessary. Sometimes some bigger assumptions are made, so like two positivity or some Schwarz inequality for the adjoint map. And the data processing inequality means that the application of channels can only decrease distinguishability of states. So now for the classical Renyi relative entropies, these were defined by Renyi for probability measures over a finite set. And this is a unique family of divergences which satisfy a set of axioms proposed by Renyi. And they have become the fundamental quantities which appear a lot in information theory. And they are defined for all alphas, non-negative or positive alphas, except alpha equal to 1. And in the limit alpha going to 1, we obtain the relative entropy, which may be seen as the fundamental divergence of information theory. Okay. So now these divergences were extended to density matrices. First, the relative entropy. This is the definition of Umegaki relative entropy. And the standard Renyi relative entropies, or they are now called the standard Renyi relative entropies or the PETS relative entropies. So if you look at these expressions, they seem fairly straightforward comparing to the classical versions, but it's not so easy to show that they really have all these good properties and that they are really reasonable. but it turns out that they really do have important interpretations in hypothesis testing, for example. And the relative entropy is again here obtained as a limit of the standard Renyi relative entropies. And also the data processing inequality holds for, but alpha has to be reduced to this interval. And here the channels are assumed to be at least satisfying this Schwarz inequality. More recently, another version of Renyi relative entropies appeared, which is called the sandwiched Renyi relative entropies. The name just comes from the fact that here one of these density matrices is sandwiched between these products of powers of the other. And it turns out that this again is a very reasonable thing to do. So first of all, it is easy to see that if rho and sigma commute, that we obtain the same expression as for the standard ones. And it turned out that this is also reasonable because it has an interpretation in hypothesis testing, but in a slightly different context than the standard ones. The relative entropy is again obtained as a limit for alpha going to 1. And the data processing inequality holds. But again, we have to restrict alpha to some interval. The quantum information theory still works mostly in finite dimensions, but it makes sense to ask about extensions to normal states of a von Neumann algebra, since there are systems for which finite dimensions is not enough, and also these divergences or these relative entropies have applications in other parts like quantum field theory and so on. So therefore, it's important to look on such extensions. So the relative entropy was extended a long time ago by Araki. Also, the standard Renyi relative entropies were introduced in this setting again by Petz, using a family of quasi-entropies, which, or sometimes they are now called the standard F divergences. Then the sandwich Renyi relative entropies were also introduced in this setting, and this will be the topic of this talk. And let me just mention that there are other versions which are defined using other versions of F divergences like maximal or measured, and one can find a lot about this in a new monograph by Renyi. So now it's perhaps the time to give you some outline of the talk. First, I will talk about the possible definitions of the sandwich Renyi relative entropies from noncommutative LP spaces. There will be several ways how to introduce them, but all of these ways use some version of noncommutative LP space. Then in the other part, in the next part, I will concentrate on the data processing inequality, which will be now proved for all positive channels, so in the channels in the weakest possible sense. And in the last part, I will look at what happens if actually equality is attained. I'm sorry, this is not good. If equality is attained in the DPI. I'm sorry for this mess. Okay, so first let me speak about the possible definitions on sandwich Renyi relative entropies and some of their properties. So the first definition is given in this general setting where M is a von Neumann algebra. We have this predual, and we take any representation of M on a Hilbert space. And we assume that rho and sigma are two normal states, or more generally normal positive functionals, and I will always assume that the sigma is faithful, but this assumption can be removed by a bit of technicality. So, but this will always be assumed here. And I also another assumption is that this row has a vector representative in the Hilbert space H, so it can be given in this form. And in this setting, the important tool is a spatial derivative. So in general, we don't, of course, don't have density operators, so we will use this instead. In this setting, the standard Renyi relative entropies can be introduced using this, spatial derivative like this. And also the Araki relative entropy has this expression and can be obtained as a limit value for alpha going to 1, as we had in the finite dimensional case. And also the data processing inequality holds for these restricted values of parameters. And here we have to assume that the channels are at least satisfy the Schwarz inequality. So positivity was not enough for these proofs which were given here. So now for the sandwiched Renyi relative entropy. So this is the definition by Berta, Scholz, and Tomamikel given quite recently. And it's given in terms of this value Q tilde alpha, which is defined by using a norm on the representing Hilbert space. Here I use this BST like Berta, Scholz, and Tomamikel because there will appear some different norms, and their definition is essentially the Araki-Masuda LP norm with respect to the commutant of n, and there are these two expressions: one for p larger than 2, or the one now for one for p less than 2. Okay, so in this definition, Berta, Scholz, and Tomamikel were able to prove some properties. First of all, it is well defined, so it does not depend on the representation or the representing vector. In finite dimensions, it really is equal to the expression for the sandwiched Renyi relative entropy. And they also found this inequality with respect to standard Renyi relative entropies, and also the data processing inequality with respect to completely positive channels was proved. They also obtained some limit values. So for the Araki relative entropy, again, we obtained it as a limit, but now here are the sandwiched Renyi entropies. And the other limit values are for alpha going to infinity, is this D max, which again is important in some applications. And on the other end, we obtain minus log of the Ullmann fidelity, which is again a well-known quantity in information theory. So now I will go to another definition, which uses some special representation, so some special standard form. So here I will denote the Hager group LP spaces always by LPM. This will be the norm. And here then M is isomorphic to L infinity M. The predual is isomorphic to L1M, and this will be this isomorphism. So I will always identify the predual with this L1M, so I will use these two expressions, so both of them. And here is the trace functional of L1M. It's just the value of the functional at 1. And L2M is a Hilbert space with respect to this inner product, and we can use the standard form where the algebra M is represented on the Hilbert space L2M by the left multiplication, And here J, the modular conjugation, is just taking the adjoint, and the natural positive cone is the cone of positive elements in L2M. And in this setting, each positive normal functional has a unique vector representative in this natural cone, which is just the square root of this operator. So this is the operator which corresponds to our so using these LP spaces, we can so define, or Kosaki defined a family of LP spaces with respect to a faithful state or normal positive functional. This will be our sigma. So in fact, this is a whole family of LP spaces parameterized by this eta. So first we can define a continuous embedding of M into the per dual by using so this this way, and then we can apply interpolation for these two spaces and define the Kosaki LP space of M with respect to sigma as the interpolation space here. This is always a dense subspace in L1M. And for if we take Q to be the dual parameter to P, then we see that we have an isometric isomorphism of LPM onto this LP space, so given like this. From this family of Kosaki LP spaces, we will use two possibilities. For first, the right LP space where eta is equal to 1. And one can see that this is the subspace of all elements in L1M which have this form. Here K is some element of the LP space, and the norm of this product, which will be denoted here by this R, is just the norm of K. The other possibility which we will use is given for eta equal to 1/2. This will be called a symmetric LP spaces, and again we have an isomorphism with the LP space given by this. And the corresponding norm will be just denoted by this P sigma. And so now, using the symmetric LP spaces, we can obtain a different definition for the sandwich Renyi entropies in terms of this Q tilde. So to obtain the entropy from this Q tilde, we just take the log and we multiply by 1 over alpha minus 1. And here this Q tilde is given just like the norm of this H row in this LP, with respect to this LP space, with respect to sigma. Note that this, of course, if this does not belong to this L alpha space, then this is just infinity, and the correspondingly the relative entropy is infinite. Indeed, this is finite if and only if for some mu, this H row, this operator has this form. For some, this mu is a positive normal functional, and the norm here, or this Q tilde, is just mu of 1. So formally we can write H mu like this, and this gets us directly to the form we had in a finite dimensional situation. We can get another expression for alpha in this other interval, so between 1/2 and 1. And here we can directly write it as a 2 alpha norm of this operator here. This is always finite because this, by Hölder inequality, this always belongs to this subspace. And we can also relate some positive functional mu to sigma and rho, such that the Q tilde alpha is just the trace of this H mu. Yeah, okay, we can also get another expression. So, okay, so let me first tell you that the difference here for alpha larger than 1, which with respect to the definition of by Berta-Scholz and Tomamical, is that here the norms are defined on the L1M, so on the predual, while they define their norms on the representing Hilbert space, which so sometimes it's convenient to use this definition or their definition. So it depends on the context. Okay, so and we can using Kosaki right LP spaces, we can put them into one framework of interpolation spaces. And here we albet these L2M into L1M using so this expression. And then we use the Kosaki right LP norm of this to define the Q tilde alpha. And so this again, this is a norm defined on the representing Hilbert space for the standard representation which we had here. Okay, I'm sorry, but there is yet another expression which is a variational expression for this Q tilde alpha. So for alpha larger than 1, one can see that so this gamma is just the dual parameter. So this is nothing more than the duality of the two norms. And this is an extension of a formula given by Frank and Lee by infinite dimensions. Which will be more useful for us is this expression for alpha less than 1. Here, gamma is a parameter which is larger than 1. This expression was obtained by Hiai. And again, it can be written here. Notice that it can be written in terms of the symmetric LP space with respect to sigma. So for these definitions, we obtain some further properties like the strict positivity for states or for if the trace is the same. Then strict monotonicity with respect to alpha. Then there is some relations to standard Renyi relative entropy. So we had the upper bound by Berta-Scholz and Tomamical, which here can be proved just by interpolation. And by simple Hölder inequality, we obtain also this lower bound, which is sometimes really useful. Then another properties are joint lower semi-continuity on the predual. Then there are some order relations. So if we have some ordering of the sigmas, then we get an opposite ordering of the relative entropies. But for the ordering of the rows, we have different things for alpha larger than 1 and alpha smaller than 1. And we also have the data processing inequality for positive channels, and this will be the content of the next part of the talk. So here, the channel is always a positive trace preserving map, so between the preduals, but usually, or sometimes the channel is defined as its adjoint, so it's like a Heisenberg and Schrödinger picture, so the adjoint is a positive unital normal map. And here, a very important thing is the Petz dual, which is a map from M to N, which is defined by this, yes, for each x, so by this equality. And this is well defined, and it is a positive normal unital map. And it's N positive if and only if this channel T is N positive. And its pre-adjoint, T sigma, is called the Petz recovery map. It goes in the opposite direction to T, and hopefully we will get to understand why it's called the recovery map. And one can also see that the Petz dual for this T sigma is the adjoint of T. So there is a mutual duality. We can look at it in this diagram. So here we have these isometric isomorphisms here with respect to sigma and here with respect to T sigma, which map M onto the L infinity spaces. And from these diagrams, this is for T and Petz dual, here the Petz recovery map and the adjoint. And this shows in particular that T always maps the L infinity space into L infinity space. And here, if we look at the L infinity norm, we see that this is just norm of this dual applied to X. And since this is a positive unital map, it is always a contraction. So we obtain from here that T is always contractive on the L infinity spaces. And since we know that this is also true for P equal to 1, so this is well known, we can just apply interpolation of the restoring theorem to obtain that T is always a contraction for every P. So in fact, this gives us the data processing inequality for positive channels for all alphas larger than 1. So what happens if alpha is smaller than 1? We can use the variational formula given by Hi. So it's just written here. And it's okay. So here we just plug in this T for any strictly positive element Y here. We just plug in T star Y. So then we use Choi inequality just to put this -1 here. Then we use the relation of that this is the Petz dual of this map, and then we use the previous results on this norm. So this gamma here is larger than 1, and you know, taking all this together, we obtain this inequality, which implies data processing inequality also for so in this interval. So putting all together, we get these results. And what is interesting here, this holds for any trace preserving positive map, and if we take the limit alpha going to 1, we obtain the same result for the Araki relative entropy, which sort of is more general than the data processing inequality obtained before, because it was always assumed something more, so positivity was not enough. And now for the last part of this talk, I will look at equality in DPI and reversibility of channels. So what I mean by reversibility of channels, so I have a channel here, and we can say that it is reversible with respect to a pair of states, rho and sigma, if there exists a recovery map, so a channel going in the opposite direction, such that both rho and sigma are recovered by this channel. And from now, I have to assume that the channel is too positive, so only positivity will be not enough for the results in this section. And we can formulate the reversibility problem in the following way. So let the D be some divergence, which then satisfies DPI for given channels. Then reversibility implies that we actually have to have equality in DPI. And the question is whether the converse is true. So whether it holds that if we have if the divergence is finite, if this equality implies that it is reversible and we can find a recovery map. It was proved by Petz that this is indeed true for Araki relative entropy. Okay. And so he called this, he did not use the word reversibility, but sufficiency by, because it's somehow related to sufficient statistics in classical statistics. And it was proved also for other divergences, in particular for standard Renyi entropies for these values of alpha, and a large number of these standard F divergences. But there are also instances when this is not true. For example, for these limit values of the standard Renyi entropies, or for this essentially fidelity. So the question is whether this is true for the sandwich Renyi entropies. To show you why this question is important, I can give you perhaps the most important applications. It is the relation of strong subadditivity of entropy and Markov states. So here M is an algebra of bounded operators on a Hilbert space, which has three parts. And the strong subadditivity of entropy was proved by Lieb and Yoskay. So this is this inequality, and it can be written in this slightly different form using the Araki relative entropies, and in which this inequality follows by the DPI when we take the channel to be the partial trace over the C system. And equality in here implies that there exists a recovery map, which means that the state ABC is recovered from this reduced state by using a recovery map just on the B part. So such states are called Markov or short Markov chains. So there are many properties of these reversible channels and their relations to states, and there are a lot of results, mostly proven by PETs, about characterizations of such situation. And one important result is the existence of universal recovery map, which means that if T is reversible with respect to rho and sigma, if and only if the state rho is recovered by this PET's recovery map. So we notice that the T sigma is always a channel, and it always recovers sigma. So if this happens, then we have a recovery map, but also the converse is true. So if we have a recovery map, we can always take it is to be to T sigma. So that's why it's called the PET recovery map. And here we see that rho is required to be the invariant state of this channel, which has faithful invariant state sigma. So we can use the mean ergodic theorem, which says that there exists a conditional expectation, which is a conditional expectation onto the set of fixed points of this adjoint here. And then rho is an invariant state for this composition if and only if it's preserved by this conditional expectation. So we can see that there is some structure in this state rho, which is connected with this condition. So in the rest of the talk, I will speak about reversibility problem for the sandwich Renyi entropies. So for alpha larger than 1, we can reformulate the problem as follows. So we take any p larger than 1, or alpha, if you like, and we assume that this element is in LPM sigma, which means that the corresponding relative entropy is finite. And then the question is whether the fact that the channel preserves this norm is equivalent to the fact that this composition preserves this operator, or equivalently the conditional expectation preserves this operator. So we can make some remarks. We can observe that, of course, this direction follows from the facts that T sigma is always a contraction with respect to NEP. So this is easy. Another observation is that that T sigma defines an adjoint of T with respect to the duality of these two LP and LQ spaces. And then we see that this equivalence holds for P equal to 2, since this is a Hilbert space, and so this is a contraction which preserves the norm of some element, and this is its adjoint. So this, I think, is well known that this is equivalent. So these two things are equivalent. So we have shown the reversibility problem holds for alpha equal to 2. So, but what for with other alphas? For this, we will use some properties of conditional expectations and LP spaces. So let E be a conditional expectation with range M0. It was proved by Jung and Fu that we may, first of all, we may identify LP M0 with a subspace in LP, and conditional expectation extends to a contractive projections of LP with range this LP0. And there is this extended conditional expectation have this bimodule property similar to the usual conditional expectation on the algebra. And it follows that if sigma is a state which is preserved by this conditional expectation, then actually it maps it projects the LP spaces with respect to sigma on M onto the LP spaces with respect to the restriction of sigma on M0. So, okay, so now we return to our proof. Here we take this state or functional H row, and we have this functional mu such that this operator has this form, and we interpolate it. So for every t between 0 and 1, we define this operator, and we consider for each t these two equalities. And we observe that any of the equalities has the property that if it is true for any t in this open interval, then it has to hold for all of these elements. So this first is by interpolation, and this is from the properties of the conditional expectation. And since we know that these two are equivalent for t equal to 1/2, and we see that equivalence holds for all elements t, and this gives us the result that we have the reversibility for all alpha larger than 1. So for alpha smaller than 1, we can use a similar trick with the conditional expectation. So here we again have some mu related to sigma and rho and alpha, and using the extended conditional expectation, we see that we have this if and only if we have this equality for mu, and we can show that this equality is equivalent to equality of these q tildes using the variational formula for q tilde, which, okay, so it can be seen in the case that we have this majorization between sigma and rho. Then this variational formula here has this infimum here is attained at a unique point here, a unique strictly positive x, and this element is related to mu, and from this and the results which we had for alpha larger than 1, we obtained the equivalence. And in general case, we use some limit arguments and uniform convexity of the LP spaces. So from this, we obtained the final theorem, which now is that if the sandwich Renyi relative entropy is finite and alpha is in these open intervals, then T is reversible with respect to this pair if and only if the equality in dpi is attained. And Okay, so that's all I wanted to tell you today, and thank you very much for your attention.
Thank you very much. Any questions, please?
I have a question. At some point, you had some M naught, like the range of the projection you were considering. And was this the one given by Kummerer and Nagel? Or
you mean here?
yeah, so the M naught was some subalgebra.
Yeah, that's here. This E is just the conditional expectation with range M, and I assume that it preserves this sigma, but it's not necessarily the one which I use, but it's any conditional expectation. So this is some general property of conditional expectations and their extensions to other LP spaces.
Okay, but then the expectation then in the slide before was, well, was it construct? No, well, 2 slides before then.
Yeah, this was, yes, this is constructed by the Kummerer and Nagel Miner-Godik theorem. This is the special conditional expectation given for this channel here.
Okay, thanks.
Any other questions, please? Comments?
If I can, Boguslav, Raffaella. So Hannah, it's maybe a naive question, but so summing up, so comparing the standard Renyi relative entropies and the sandwiched ones, so you think that they, the sandwich one can be more powerful in sufficiency problems or hypothesis testing, since you are an expert there, or
it is for the hypothesis testing, the sandwich Renyi entropies is used in a slightly different context. So so they both are, so both the standard and the sandwiched Renyi relative entropies are necessary to describe the full, so they describe the error exponents, but okay, but in slightly different settings. And as for reversibility, we have the same result also for the standard ones in a given interval. So, but there the proof is completely different. So here we had to use some different techniques. And what is maybe interesting for the sandwiched relative entropies is that this DPI with respect to positive channels, because as I was aware, then until now, the DPIs were always proved with respect to completely positive channels, or at least something more was always assumed and was really needed in the proofs. And here it works for only positive channels, and it implies that the same is true for the Araki relative entropy. I think this is sort of new. So at least in the context of general von Neumann algebras.
Yes, and indeed, if we think about the hypercontractivity and Log-Sobolev inequality results, I'm thinking about the paper by Boguslav and Robert Olkiewicz. The sandwich norms seem to be more powerful, and I think one of the reasons is because they preserve positivity in a better way, among other things, because
I think that's a very, very interesting relation.
I have a question.
Yeah.
So in the inequalities such as DPI, is anything known about the maximizers, extremizers of the inequalities?
Of the, sorry, for
The
can
extremizers,
you,
is something known about them?
I'm sorry, I did not understand.
Arthur, you don't have a good connection, I think. We don't hear you well.
I'm sorry.
Well, now it seems better, but
Try again, please. We don't hear anything.
No.
So maybe in between I will ask a question. You can have a lot of such conditional expectations. Can you have some information about them, some relation between them?
In what sense? I mean,
For example, weak dependence.
Yes, yeah, I don't know. I did not think about this. So in this context, what happens?
Yeah, that's a very nice way of defining conditional expectations. If one tries to define them in a way like it would be natural in statistical mechanics, that you consider some finite volume states and then pass to the limit with corresponding conditional expectations. This is very hard to conquer. In particular, we don't know essentially anything about existence of the limit and how quickly the limit could be achieved, which would be very important ingredient for some analysis of Markov semigroups. That's a motivation for my question.
Yeah, unfortunately, I cannot tell you anything, but I think this is yeah. So this is a possible way also to apply this these entropies, because they are essentially LP norms, and yeah. But I cannot tell you anything more.
You also studied Ollie spaces, right? What about
A little bit,
spaces
yeah.
here?
But yeah, I don't know whether they can be related to some divergences. Yeah.
Yes, they should be, because
Of course, there is this sort of exponential Orlic space, which is related to relative entropy. But yeah, so how this comes from yeah, I'm not sure about this.
Generally you can define what entropy is if you study the flow through families of Banach spaces. And you can say that entropy from this point of view is just a tangent vector of such a flow. And you can define that in essentially whatever Banach spaces you take. You can take all these spaces, and in classical case, this is also of interest to study analogs of hypercontractivity in all these spaces, with some nice works by Roberto Barf, Catio, and that's that would be interesting to develop here as well.
Yes, this is really interesting, and yeah, if you could send me some references, I would really appreciate that.
Yeah. So we lost Arthur, or
I do have a question. I think maybe also that Arthur was hinting at in some applications the states that make that extremize the inequality. In other words, the states that have the property that the inequality is sharp, whether or not they could be characterized by some special property.
Yes, I don't know. I didn't think about this question. I'm sorry.
Because there's a corresponding result in the classical theory where the extremizers are Gaussians.
But this is for the relative entropy. So.
Yeah, right. Yeah. So,
yeah.
But I mean, it's very abstract, and so one would expect then that for the extremizers there might be explicit properties that could be. So I guess you kind of answered in that T is reversible, but if it could be made more explicit.
Yeah. Yeah. In general, I don't know. So there are also some results which show that if the difference between the relative entropy of rho sigma and this one, so the difference here, it can be somehow lower bounded by some entropy or something, some distance of between rho and this kind of recovered rho or something like this. So there are some results for this. So maybe one could refer. Okay, maybe one could get something from there, but I'm not sure.
So for many inequalities, such as the Hausdorff-Young, the biprojections play the role of the Gaussians, and I was wondering if there's something like that here.
Yeah, I'm sorry, I don't know.
Okay, any other questions? So let's thank the speaker again. Thank you very much. And we have a few minutes break. We start at 5 o'clock Istanbul